In our course selected topics in decision modeling, today we are in 20th lecture, that is heuristic methods for integer programming, right. So, let us go ahead, the heuristic methods for integer programming. We have seen different other ways of solving travelling salesman problem, but there are certain methods which could be called heuristics. Now, see, TS problem is a very typical integer programming problem. There are other integer programming problems also. There could be many other heuristics for solving them, but specifically we are going to discuss the heuristic methods for travelling salesman problem in this lecture. So, here are some of the methods like the nearest neighbor method, the subtour reversal method, greedy heuristics method, genetic algorithms and other evolutionary algorithms such as simulated annealing and so on. Certain things you must note about the heuristic methods in the very beginning. You see, if I compare the branch and bound algorithm versus heuristic methods, one thing should be very clear to you that this gives us an optimal solution, but here the optimal solution is not guaranteed, right. So, while an optimal solution is guaranteed in the branch and bound algorithm, in heuristic method the optimal solution is not guaranteed. But then you may ask, then when we have algorithms for getting optimal solutions, why are we going to do heuristic method? The reason is very simple, that these are NP hard problems. The travelling salesman problem is an NP hard problem. It means the complexity of the problem rises exponentially as the problem size increases. So, when we have a very large travelling salesman problem with number of cities very large, then it may so happen that the branch and bound or other exact algorithms becomes extremely difficult to employ. In those situations, we have the heuristics as the only option. Is it all right? So, that is the essential idea, that why we should still have the heuristic methods which does not guarantee optimal solution. Is it all right? But it also, therefore, the heuristics are methods which can quickly give us a solution, right, but it does not guarantee an optimal solution. So, this point has to be remembered, right. Another note that should also be kept in mind is that the genetic algorithms and other heuristic algorithms, they are quite involved, right, that really require certain more knowledge that we really do not have at this point in our lecture. What I have really planned is that a set of lectures are separately kept aside for the meta heuristics. Is it all right? In those lectures, we are going to discuss genetic algorithm and other evolutionary algorithms separately. Is it all right? So, in this particular lecture, we are going to discuss these methods, that is the nearest neighbor method, the subtour reversal method and the greedy heuristics method. So, let us start with the first one, that is the nearest neighbor method. So, let us take a 5 city travelling salesman problem for minimizing costs as given in the matrix below. So, how the nearest neighbor heuristic works? First of all, select a random city, that means we can start with any city. then find the nearest unvisited city and go there, is all right. And then check whether are there any unvisited cities left. If yes, repeat step 2, is all right. So, if some more cities are available, so suppose from A we have come to B, then from B again try to find out the nearest neighbor, is it all right. So, that is how you should do, and then repeat step 2 and then return to the first city, is it all right. Now, there is certain things to note here, is that while you apply the nearest neighbor heuristics, again there are certain things to note, that A to B and B to A distances may or may not be same, is it all right. So, there are problems where suppose I have a network, let's look at a particular network. So, suppose I have a network like this. Suppose we have 4 cities A, B, C, D, and we have a network like this, and in this network we have certain distances, let us call them as 4, 4, 4, 3 and 2. So, those are the distances. So, you see A to B and B to A have the same distance, is it all right, in this network, but in our matrix A to B is 10, whereas B to A is 5. So, this creates a certain difficulty, So, what is the nearest neighbor of A? What is the nearest neighbor of A? So, we have to think whether we have to go row wise or column wise. So, usually it does not matter if you have a system like this. That means, if we have a symmetric matrix where the A to B and B to A are same, in this, like in this example that I have given, A to B is 4, B to A is also 4. So, there is no confusion. So, when it is like this, whether you go row wise or column wise, it does not matter, but in the kind of situation that we have had, that A, which is the nearest, B, C, D or E, it really creates a problem whether we go row wise or column wise. So, arbitrarily I will show examples which we are selecting row wise, but it is not really necessary that you do row wise, you can also do column wise, is it all right. It also creates a problem that when you go to the last city, obviously you have to choose a distance which is beyond you, and since row wise and column wise distances are could be very different, your answer could be unexpected also suddenly, because suppose A to D is 6, but D to A is 7, right. So, look here, like A to E, just compare, A to E is 9, but E to A is only 3. So, you see, while A to E is so high, but if you go back from E to A, you really gain, right. So, these anomalies will be there if we have different distances to and fro, right. So, the problem that we have taken, we have different distances. So, there will be some anomalies of that type, but if you have a perfect problem, then probably the algorithm would work a little better. But anyhow, let us see the method, right. So, what we do in the nearest neighbor algorithm, the first of all we arbitrarily start at a city A. So, it is highlighted that we have started at a city A, and then we have all those distances. So, which is the nearest neighbor? Just see very clearly, nearest neighbor is C. So, we choose C. So, that means we have chosen C. So, now C is going to be our this thing. So, now you check from C, right. So, what we have done, look here, we have blocked A, right, we have blocked A, and while you check C, you see C to A is 4, but since you have already come from A to C, C is already taken, right. So, you cannot go back to C. If you go back to C, what will happen? Suppose you have A to C and then again go back to A, you just cannot do that, right. You just cannot do that. If you do that, there will be a problem. What is that problem? You will get a subtour. So, moment you get a subtour, then there is no point carrying on with the heuristics and there will be a difficulty. So, we cannot do that. So, what we do really? We look at the C and we block C to A, put an M there. So, you see we have block C to A is blocked by inserting M. So, we have inserted M and we have blocked C to A. Now, look at the remaining distances. Which is the minimum? It is C to D, that is 7. So, you are clear that now we should choose D, right. So, that is our second step. So, we have A gone to C and then gone to D, right. So, look here. Now, we have blocked A and C and we have come to D. So, what we have had? We have had A to C and then to D. This is what we have. Now, from A to C to D, see, look, A and C should be blocked and D is taken next. So, as A and C is blocked, again in D block distances to A and C. So, again you put this as M. Now, remaining distances, the minimum again is comes out to be this one, that is D to B, right. So, nearest neighbor is now B from D and therefore, we choose B. Is it all right? So, we choose B. So, what we get now? We have got A to C to D to B. This is what we have got. So, again now check, this time we have blocked A, C, D, all are checked, blocked and B, and again we have put all these A, C, D as M, right, and this time only one distance is left, that is E. So, that is E has to be chosen. So, E is chosen. So, right. So, we have got A, C, D and B, right. So, we have chosen like this, that is A to C to D to B. So, now obviously, when you check from E and this is the last node, now all other distances should be blocked. So, nearest neighbor will be nothing but A. So, we have to go back to A, that means A to C to D to B to E to A. So, look here, we have got a complete route and it has to be feasible, and what is D C star is 16, right. So, we have got a solution. Now, if you compare with the branch and bound solution, incidentally that solution was also A to C to D to B to E to A. So, which one was also the same solution, but do you know we got the optimal solution here. Why optimal? Because we knew it in branch and bound, we got the same solution, but then there is no such guarantee that we are going to get this kind of optimal solution all the time, right. So, let us look at one more example, that is the 6 city example. So, look at the 6 city example that we have taken earlier and see what happens there. So, if you take the 6 city example, so you see arbitrarily start at A. So, you see the nearest is C. So, nearest neighbor C. So, we choose C, right. So, we have come A to C. Now, again from C we block A. So, put an M out there, C to A, and which is the nearest neighbor? Nearest neighbor is D. So, choose D, then we got A to C to D. Then we block A and C, look at D and put all these distances to M. Now, obviously, B, E, F all are equal distance, but okay, arbitrarily choose let us say B. So, B is chosen. So, we have now got A to C to D to B, right. So, again A, C, D are all blocked, and look from B, put all these A, C, D to M. Out of the two distances, the minimum is F. So, F is chosen. So, what we got? A to C to D to B to F, right. So, all these things are obtained, and now go back, go to the next slide. Then we find that when we come to E, right. So, check from F, block F from A, C, D, B, and from F we see we have put all M. Now, only one distance is left, that is E, right. So, what we get now? We get A to C to D to B to F to E, right. Then we have no other option but to choose the E to A, because we have everything else is blocked, and this is the last node, and we have to come back to A. So, we come back to A. So, we get now A to C to D to B to F to E to A. But how does this solution compares with the best possible solution? Is all right. Look here, when we compare this with the branch and bound solution, that is A to C to E to F to D to B to A, we find that total TC star was 87, right. So, if you really look at what is the solution that we have had in our branch and bound, we found that the optimal solution there was having a TC star 87, but here our TC star is 114, which is not good. Obviously, when we have 87, getting 114 through the nearest neighbor method is not that good at all. Obviously, one of the reasons why it happened is if you compare A to F and A to E, obviously A to E and E to A was 50-50, but then not in every other case, right. There are cases where the distances are very different, because the way we have optimized everything, but the last leg, that is E to A, we had no choice, we had to choose it, right. So, that really created imbalance, and obviously, we did not get a very good solution. So, a good solution is really not guaranteed by the nearest neighbor method. Sometimes the heuristic may return not so good solution, right. So, and we may have to live with that. Fine, let us see the other algorithms. Let us look at the next one. This is called the subroute reversal heuristics. So, here is a problem, that is a 7 city problem, and we start with, see, look here, that 7 city problem, just imagine if we have to even solve by branch and bound by hand, it is not going to be easy, right. We may have to branch quite a bit, right, may have to branch quite a bit, whereas the subtour reversal can give us a quick solution. Even minimum the neighborhood, the nearest neighborhood algorithm can also give us a quick solution, no problem at all. So, here start with any feasible initial trial solution, and then for the current trial solution consider all possible ways to performing a subtour reversal, not entire tour. So, what is a subtour reversal? I will explain. Then select the one that gives the largest decrease, right. So, basically start with a feasible solution, trial solution, then keep doing subtour reversals, obviously not the complete tour reversal, that you should avoid, and then see what is the minimum that you get, and then stop when no further reversal improve the current trial solution, right. So, that is very interesting. Let us see how it works. So, arbitrarily supposing you choose 1 to 2, see all those highlighted, that is 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7 and 7 to 1. Now, why did we choose it? Because it is so easy to choose, that is the reason, no other reason, that it is so easy to choose, that is 1 to 2 to 3 to 4 to 5 to 6 to 7 to 1. So, that is how we started. It is not that you have to start like that, you can randomly choose anything and you can start with that. So, when we started with that, if you add them all, you get 20, 31, 42, 48, 57, 69. So, total distance 69. This is definitely feasible solution. So, that is the beginning solution for us. Now, suppose we reverse 2, 3. So, you see what happens, this is, suppose this is node 1, this is node 2, then node 3. So, we are taking in this way 3 to 4 etcetera, right. So, if we reverse, then what you do is, you see, we then connect 1 to 3 and 3 to 2 and 2 to 4. See the difference. Earlier it was 1 to 2, 2 to 3, 3 to 4, right. Now, it has become 1 to 3. So, 2 to 3 becomes now 3 to 2. So, 1 to 3, 3 to 2, 2 to 4, 1 to 3, 3 to 2, 2 to 4. That is exactly what is shown here. See 1 to 3, 3 to 2 and 2 to 4, right. So, earlier it was 12 plus 8 plus 11 plus dot dot dot. So, 12 plus 8 plus 11 plus dot 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 replaced by 10 plus 8 plus 12 plus dot dot dot. So, that means earlier it was 31 plus dot dot dot, now it is 30 plus dot dot dot. So, what is the difference? Your guess is right. Now, the new root is 1 less, is all right. So, you see 1, 3, 2, 4, 5, 6, 7, 1 is a feasible root, and this root has a TD star equal to 68, which is 1 less. So, we see by subtour reversal we have got one more root that is better than the original. The question is, will it always be like that? Answer is no. No. By subtour reversal there is no such guarantee that you get a better root. In fact, you may get a worse root also. So, there is no such guarantee that you do subtour reversal and like magic you get something better, right. But if you keep on doing those subtour reversals, see how many options you have. You can reverse 2 3, you can reverse 3 4, you can reverse 4 5, you can reverse 5 6, you can reverse 6 7, right. So, you can do, and then later on you can reverse 2 3 4, 3 4 5, 4 5 6, 5 6 7 etcetera etcetera. So, you can keep on doing like this, you can do different subtour reversals and then you can get something which is better than what you started with, right. So, this is the mechanism etcetera, and how many different options you may have to go through. The number is going to increase with the size of the problem, but still this is not a big calculation really. So, obviously, it is not going to be that difficult. So, you see a chart has been prepared as a iteration 1. The original was 1 2 3 4 5 6 7 1, the TD star was 69, that was the starting with. If you reverse 2 3, you get 1 3 2 4 5 6 7 1, you get TD star 68. If you reverse 3 4, you will get 1 2 4 3 5 6 7 1. Look here, this 3 4, look 3 4 has been reversed to 4 3, all right. Then you get TD star 65, all right. So, can you locate this one? You see 1 to 2, 2 to 4, then 4 to 3, 3 to 5, 5 to 6, 6 to 7, 7 to 1. So, you add them 24, 35, 38, 44, 53, 65. So, you get 65. If you reverse 4 5, again you get 65. If you reverse 5 6, you get 66. So, the lowest one is your 3 4 reversal, and then we have now 1 2 4 3 5 6 7 1, and we have a TD star of 65. So, this is what we have got by iteration 1, right. So, basically started arbitrarily with some root, keep on doing reversals, and we get a better solution, the best one we choose. So, that is the first iteration. Now, in the second iteration, now you see this is your original, and that is what you got in the last slide. Now, in the second iteration, if you reverse 3 5 6, right, if you reverse 3 5 6, so look here, this is our 3 5 6, if you reverse then you get 6 5 3. This time it is shown here 1 to 2, 2 to 4, 4 to 6, right, 4 to 6, then 6 to 5, 5 to 3, 3 to 7, and 7 to 1. So, if you add them up, you get 64, right. So, this time the base solution becomes 1 to 2, 2 to 4, 4 to 6, 6 to 5, 5 to 3, 3 to 7, and 7 to 1, and that is 64. So, this is our base solution obtained so far, right, but this is still not optimal. See, the optimal solution is really 1 to 2 to 4 to 6 to 7 to 5 to 3 to 1 with a TD star equal to 63, or there is one more which is also giving TD star equal to 63. But this improvement, you see I have not shown further iterations. So, further improvements not possible in this particular problem. So, what happens, we have to be happy with a less near optimal. So, this is not optimal, this is really near optimal. So, all these heuristic methods can really give near optimal. So, a quick way we can reach the near optimal and we can work with a very good solution, right. So, that is the advantage of the heuristics. Good. So, let us look at one more, that is called the greedy heuristics. So, what is the greedy heuristics? Really is a very simple method. You sort all the edges, select the shortest edge and add it to the tour. It should not create a cycle of less than n edges or increase the degree of any node to more than 2, is all right. So, do we have n edges in our tour? If not, repeat step 2. So, really speaking, what it does, you sort all the tour and then choose the shortest, but then add something in such a manner so that you really have a complete tour sort of thing. Say, let us give an example. Supposing I have chosen, let us say A to B. So, this is chosen. Now, can you choose B to A? No. Why? Because it gives us subtour. This is subtour, not possible, right. We have chosen A to B. Can I choose A to C? No, because then you see C to A is okay, but A to C is not okay, is all right, because you see you cannot go simultaneously from A to B and A to C. What it does is basically increase the degree of node more than 2, right. So, A has to come from somewhere, maybe C. So, if again A to C, then what will happen, this degree becomes 3. So, this is not allowed, right. Also another thing is not allowed, not written here. We have A to B to C. Can you have A to C again? Answer is no, right, because if you have A to C, again this is the same problem, because A has to come from somewhere, maybe D. So, look here, this is the difficulty, this is the degree increases more than 3. In other words, it will do not get complete tour. So, that means you sort the edges and take the shortest one, but take the next ones in such a manner that first of all no subtours are there, first then it should not disturb the tour by any other way. That is the way we should proceed. So, that is the greedy heuristic. So, let us see what we do. So, shortest edge, if you look here, is dB. So, take dB, right, dB length 1. So, very clear that we should choose dB, right. Next shortest edge is BE or EB, right. So, we can, there is no problem, let us choose E. So, BE. So, we get D to B to E. Next is EB. Can you choose EB? We cannot, because in that case we make like this. So, you see subtour is obtained, not possible. So, we cannot take EB, right, EB not possible. So, we got D to B to E, right. So, that is the first. Next, again if you go further, the what is the next shortest? It is A to C or D to C or E to A, right, length 3. DC not possible, because look here we have already chosen D to B to E. Can you choose D to C? Not possible, because then same problem as I have explained earlier, not possible. So, we can choose AC, obviously yes. We can also choose EA, right. So, we can choose both. So, when you choose, we get already D to B to E to A to C, right. Now, obviously, we have to choose C to E, C to D, then there is no other option, because we have to make it a closed tour. So, we choose that, and when you do that, if you written differently, this is A C D B A C, and what is the TD? TD will be 32713, total distance is going to be 16. So, this was our optimal solution in BNB method as well, is all right. So, by greedy heuristic also we can quickly find the TSP solution, but once again there is no guarantee that we are going to have the shortest possible path, right. It could be a complete tour, definitely it will be a feasible solution, but there is no guarantee that will be the optimal as well. So, these are the weakness of the heuristic methods, and that is how we solve such problems. So, in our integer programming we have seen the different formulations, different ways of solving integer programming problems like cutting plane algorithms, branch and bound algorithms, heuristic methods, and so on and so forth, right. So, in our next lecture we begin a new topic on nonlinear programming. So, thank you very much.